Okay. Good morning, everyone. First of all, I want to thank the organizers of this workshop very much, especially Daniel, for inviting me, especially since I'm no longer in academia, but I'm still here today to present some of my PhD work and also the work of my collaborators, of course.
Yep, tell the microphone very close.
Like this. Yeah. All right. That sounds better. But it's, yeah, maybe if you understand me like this, it's maybe better to not use. Okay. All right, so my talk will be about modeling environments of evolved stars. So I've heard it's been a lot about disks this week, but I'm going to talk about something else, and we'll be modeling these environments using phantom and also surrogates. Okay, next. To sketch a little bit the context we're talking about, so this is a general overview of stellar evolution. I think you all know this, and I'll be talking about these asymptotic giant branch stars, which is basically the evolved version of solar-like stars. To sketch a little bit how they are, they're pretty huge, bright, and also cool because they have a large radius. They're 1,000 times as bright as the sun, and their surface temperature is about 2000 Kelvin. And also these stars are very puffed up because they have a large convective envelope and only a tiny core, although this core is about half of the mass of these stars. And this is an interesting structure because this convective envelope, there's a lot of movement going on, and this can penetrate some of the layers that are still burning nuclear species. And by this, S processes happen to exist inside these HB stars. And if you take a look at the periodic table, this is very important because we see here these dying low mass stars, which is basically the HB stars, and they make a big, an important contribution to some of these elements, for example, the S process elements. But also you can see here, there are quite some elements where HB stars are a very important contributor. And apart from this, also HB stars are a very important contributor to the enrichment of the interstellar medium by the gas and the dust they provide to this interstellar medium. So this makes that HB stars play an important role in the life cycle of galaxies because they provide important building blocks for new generations of stars and planets. And therefore, if we want to understand the life cycles of galaxies well, we also need to understand these HB stars very well. So this is the context why it is interesting and important to study the HB stars. If we go a little bit into detail, another important part about these HB stars is that they harbor a stellar wind. And this stellar wind is of great importance. Maybe Owen Vermeulen has talked a little bit about this yesterday, so it will be a bit of a repetition, but a bit of repetition is never too bad. So these stars, these HB stars at their surface, there are pulsations happening, and this makes that some of the material is lifted higher up in the atmosphere. And a bit higher up, the environment is cooler, and therefore dust is able to condensate. So there are dust grains present around these HB stars. Now it happens that these HB stars, they shine in the infrared, and it happens to be that it's specifically the radiation that these dust grains can absorb and thereby get accelerated outwards. When they get accelerated outwards, they drag along the gas, and in this way, there is a macroscopic outflow happening at the surface of the HB stars. So in this way, there is a huge circumstellar envelope that is formed around these HB stars. And it's a specific envelope, so this environment, as I said in the beginning, that I will be talking about further. So in the rest of my talk, I will not look at the details of the HB star anymore. So we say that HB star has a certain massless rate and that there is a circumstellar envelope expanding at a certain velocity. So these are the two main important parameters we take into account when talking about these circumstellar envelopes. Now there's two other important ingredients actually that we need to include in this picture. And it's the following two. So first of all, the HB star shines. So we need to include some radiation processes. And there's another important thing is that within these circumstellar envelopes, there's a lot of molecules present. So therefore, we also need to incorporate astrochemistry within this picture. And also these molecules makes that the environment can heat or cool. So again, there are these radiative processes we need to take care of. All right, so I've been now sketching a nice and theoretical picture of AGB outflows. However, as I sketched it, it was nicely spherically symmetric, but the recent observations, this is with the ALMA telescope, have shown us that this is actually not the case. So what we see here is 10 observations of different AGB stars, and these are observations of the circumstellar envelope. So the AGB star is every time located in the very center of these observations. And we see a lot of structures here. So it's not nicely spherically symmetric. We see some morphology happening. And of course, we've been wondering what can be the cause of these structures. And the community is, we think or we believe that there's actually companions present around this EGB star. So if we take a look at this sketch again, we believe now that there is a companion embedded in the dusty circumstellar envelope. And of course, then we have an orbit. And in this way, the material gets sort of gravitationally attracted and gets structured somehow in sort of a spiral structure like this, for example. So that's what we believe is happening within the AGB outflows. And of course, this can have a big impact on what we have researched earlier when we were assuming that these outflows were nicely spherically symmetric. So for example, it can impact the properties of the circumstellar envelope itself. So for example, this mass loss rate and the expansion velocity, if we reduce these values from observations, assuming the whole thing was spherically symmetric, it might be different than when there is like structure going on. This can go further and further. It can impact, of course, the chemistry, the molecular abundances of the outflow, and hence also the enrichment of the interstellar medium. Maybe even the presence of a companion can also impact the stellar evolution of the AGB star itself, or the other way around. So also the nuclear processes can have different yields than we've been believing so far. So in the end, the fact that these AGB stars exhibit some kind of morphology can impact the life cycle of galaxies. Then there's even another open question we want to assess here. Here you can see some planetary nebulae, and the planetary nebulae are a subsequent evolutionary phase of the AGB star. And from these, it's well known that these are, that they have crazy structures sometimes. And we also wonder if there is a link with the structures that we see now in AGB outflows. Because it's not a coincidence, we think, that they have sometimes similar structures. So this is, again, an open question. And therefore, we need to study these EGB stars well. And now, how do we do this? Of course, it's with modeling. Otherwise, I wouldn't be here. So if we have our system again, we actually need different ingredients to model properly this circumstellar envelope. First of all, of course, we need hydrodynamics to assess all these density structures we see. And this we do with Phantom. Therefore, I'm here. And so the NLCS, who will talk tomorrow, has incorporated a wind launching mechanism in Phantom, and also Mats Esselders, who talked last year, I think, at this workshop, enhanced this process. So therefore, we already have a good Phantom code to model these AGB outflows. Next to this, as I was saying, we also need the chemistry. There's also been done a lot of work in this, so we need the chemistry for assessing the chemical abundances. And there's been done a lot of work in one dimension for chemical kinetics, mainly by Marie van de Zande, as you can see from all her papers here. And already from this, we can learn a lot about the structure of the AGB star. But of course, the big goal would be to combine the two to also assess the chemistry in 3D. And for that, I'm going to move the little screen again. For that, we need some radiative transfer and also some thermodynamics to have the connection. Now then, if we want to mimic the observations, for example, this is an observation from a spiral structure around an AGB star, we need to process how these abundances shine their light, so how they radiate. And again, we need radiative transfer to make the connection to get the emission of these molecules. And at KU Leuven, we do this using the code Magritte. So this is a ray tracing radiative transfer code developed by Frederik de Keuster, and also Thomas Kullemans is working further on this to develop it more. All right, so these are the 3 different ingredients we need to properly model such an observation, basically. And of course, we want to combine these into one big 3D model, including hydrochemistry and radiative transfer. But of course, it's a big work in process. We're not there yet. We have the different ingredients. Now we want to combine them all. And this is a little bit what I'll be talking about further. But maybe first, if we only look at the hydrodynamics, so we can already do a morphology study. So this is something I did in the beginning of my PhD. We can simulate a certain HB star with a companion at a certain distance. The companion in this case has a stellar mass. I show here the view in the in the orbital plane, but this is not just a disk; it's really a 3D structure. And we see some spirals happening, because of the interaction of the gravity of the companion and the outflow of the HB star. Now we can change the system parameters. For example, if we now take a slow wind instead of a fast wind, we immediately see that the spiral structure is already different. And in this case, this is because now the wind is slower and therefore the gravitational interaction becomes stronger because there is more time to interact with the companion. What we also tried is what if the companion now was of planetary type, and I hope it's a bit visible on this screen, but you see a slight density enhancement in a spiral structure around the HB star. So also massive planets can cause some structures. What we also see in these phantom models, this is work done by another colleague, Jorien Malfait, is that there are also accretion disks formed around the companion, and these disks are even a bit flared. As this is also an important thing already, and very slightly in the disk, you can see also some kind of a spiral structure. It's not so clear on this slide, but yes, there is also a slight spiral structure inside the accretion disk. Further, also Jorien Malfait, she experimented a bit with hierarchical triple systems, and we can see here some kind of a double spiral structure within the HB outflow. But I think the main takeaway from these studies is that all these different structures that we see, it's a very degenerate problem. So it's not that if we see a certain structure in an observation, we can really immediately say, okay, it's a companion of this mass, and the mass loss rate of the HB star will be this. So it's really degenerate, and hence we need to include the other ingredients that I was talking about to get to know the systems better. All right, so if we build towards this 3D hydro-chemical-radiative model, we actually also chemistry is slow, and also radiative transfer is very away. We get an ultra slow code, and this will make it infeasible to assess a big parameter space with modeling. So therefore, we need to go to another solution, and there is a solution, namely using surrogate models. And with surrogate models, we use emulation to process a certain thing. So what is emulation? It's sort of it's a statistical approach. It can be different kinds of statistical approaches, but this approach is then able to take a certain input value and return the same output value as a classical code would do. But the important thing is that it will do it in a much faster way. And that's the thing we want, of course. We want the same output, but in a faster way. So with surrogate models, we can do this. And at KU Leuven, we've done this for already two ingredients. So first of all, for CO line cooling within these HB circumstellar envelopes, because CO line cooling is a very important coolant inside these outflows. And then we also did this for chemical kinetics, and therefore we built Maes. I'll first cover shortly the CO line cooling. So this is work done by a colleague of mine named Thomas Keulemans. So what did they do? He started from some phantom models of these HB outflows and post-processed them with the code Magritte, so the radiative transfer code, to calculate CO line cooling. When he had all these cooling rates from CO, he performed a fit, which is not very spectacular. It's a big formula, but what's important here is that this formula contains depends only on parameters we can get from hydrodynamics. So if we can fit a bunch of models, we can later just use this formula within Phantom, and we assess the cooling rates much faster than doing the whole ray tracing throughout the radiative transfer codes. We also did an uncertainty analysis on this fit, because of course a fit, it's never perfect. We also need to assess some of the uncertainties on this. The way we did this was with a module of Magritte, namely Magritte torch, which includes some PyTorch code, and therefore we can, by that we can do a certain uncertainty analysis. So as I was been saying, if we can fit this quite easy formula, which we can process quite fast within a Phantom code, We then can include it in Phantom as a surrogate model, and this way we can assess the cooling, CO cooling rates within our outflow and already include some cooling within the outflow, and yeah, this will make the hydrodynamics more correct if we look at reality. So this is what we've done for the CO line cooling. Then the last thing I will be talking about is Maes, which is a bit the prime project of my PhD, so hence I'm including it here. So Maes stands for Machine Learning Approach to Chemistry Emulation. So as the name says, it's an emulator for chemistry. So classical, yeah, so how does chemical kinetics works? Maybe a bit short, if you don't know. So we have some physical parameters, the density, the temperature, and some radiation fields. And we start from a bunch of abundances from different molecules. We can take them and put them through a chemical kinetics code to have then the abundances updated by some time step. And what is behind this chemical kinetics is basically a bunch of coupled ordinary differential equations, which every time equates the production and the destruction of a certain chemical species. Now, what do we do with this emulator? We circumvent the classical way and we go to a surrogate model, of course. And before, for the CO line cooling, it was just a simple fit. But in this case, we will use some machine learning to assess the chemical kinetics. Yeah, it's covered again here. So, of course, the big importance of this whole surrogate model is that we get a speed up, because that's, of course, what we want. We want to have fast chemistry. All right, so for Maes, and I will talk now a bit about architecture of this emulator. So the issue with chemistry is that we have a lot of input parameters. We have the physical parameters, which is only 3, that's okay. But if you want to include a lot of species, for example, in this case, we want to include 500 different molecular species, it's quite a big parameter space. So in order to deal with this, we first use an autoencoder. And an autoencoder is used to reduce the dimensionality of a certain space. So we start from our normal space, the n vector, we can encode it using some neural networks to a latent space. And in the latent space, for example, we went from about 500 parameters to about 10. So we can really reduce the amount of parameters. And then, of course, in the end, we can decode it again with sort of inversed neural network to get our original input back. So that's our encoder part to reduce the dimensionality of our problem. Now, of course, for chemistry, we want to include some time evolution because we want to assess the change of abundance over time. And that is something we will do within the latent space. So within this latent space, we put the time evolution over a certain time step. And then in the end, we get this structure for our architecture for Maes. So we have our input parameters, the P is the physical parameters, the N are our abundances. We can encode it to a certain latent vector. We will then do the evolution. We have the updated version of our latent vector, and we can decode it again to get an update on our abundances. Now, how does this evolution work within this machine learning thing? So we will also use a certain differential equation, but the benefit is now that we're only dealing with about 10 parameters and not with the 500 from the classical mechanics. So what did we do within this latent space? So the classical mechanics, classical chemistry, the differential equations looks like a polynomial, and we actually are inspired by just the form of this formula, and we used it in our latent space. But now it's important that these coefficients are trainable. So within our whole Maes architecture, we train the neural networks within our autoencoder, and we also train these coefficients to get a certain model, a surrogate model that fits the whole chemistry, the chemistry space. So this brings me again to the whole structure. So in the end, we get predictions of the abundances. Now, of course, there is a whole process in building this thing using training, as I was already mentioning. So the whole process went like this. So we have a certain input of very many different chemical models. We can each time make predictions using Maes. We can compare then the predictions to what we see in 1D chemistry, because of course there is no 3D chemistry yet, so we cannot really compare to 3D chemistry. So we need to use what we have, which is the 1D chemistry. And of course, this is a very big loop in order to really train the Maes surrogate model. All right, so this brings me to some results of Maes. So what you can see here is an abundance, chemical abundances of different molecules. Our HB star is located somewhere here on your left-hand side, and we are looking outwards in the outflow. For example, we see that there's quite a lot of CO, which is this line. And so this is what a classical chemical kinetics model gives us. And now this is what Maes can do. So as you can see, Maes can predict with the machine learning very well these abundances. So this was a very nice result we got. So we see that Maes works for at least one D chemistry within HB outflows. And of course, it's very important to note that Maes is not only able to predict correct chemical abundances, but of course also in a shorter calculation time. So only in 5% of the time of a classical model, Maes can predict the same things, the same abundances, or close to at least. So this was very nice. All right, this already brings me to the conclusions of this talk. So from hydrodynamics only, we can already learn a lot about these HB systems when we include companions, because we get all these different morphologies, and we know a little bit about the physics behind it. So already this is very useful, but of course we need to assess the other ingredients as well, namely the radiative cooling and chemistry. And what we did at KU Leuven is showing that it's actually possible to do this using surrogate models. So we already have, I see the slides are a bit slower on Zoom, but I hope it's not too bad. So we built surrogate models, for example, for the radiative cooler for CO lines and also for chemistry. And this seems to work, but of course, this is not the end of the story. There is still a bit of future work to be done. Okay, my Zoom is reconnecting. Sorry for the people online. Shall I just continue or?
Yeah, Jerome is a bit sketchy sometimes. It might reconnect alone.
Yeah, okay. So to end my talk, there is still a lot of future work to be done. First of all, we have now Maes, but it only works in a 1D, in a 1D framework. So we need to couple it to Phantom, to the hydrodynamics, to also make it work in a 3D context. And this is something Camille will talk about in a bit. And of course, in the end, we want to build towards this comprehensive model for circumstellar envelopes, including the hydro, the chemistry, and the radiation in 3D, as I mentioned. It's a bit of a step-to-step approach. There are still other different things that need to be implemented. For example, wind launching. I think Owen talked about it yesterday a little bit. And then the chemistry, as I mentioned, the radiation. Also, we have these pulsations at the surface. It's also something we need to still include in this big model. And then maybe also some orbital evolution, because of course, the orbit of the companion might change over time when there's interaction. So in the end, if we have this all together in a fast code, we can hopefully make correct predictions of, for example, mass loss rates of circumstellar envelopes, also the chemical yields, elemental yields. Hopefully we can predict them more correctly than we're doing now. And in the end, we can hopefully assess better of the galaxy, incorporating all the information of the HB stars. So thank you very much for listening. This was also work by my collaborators. And if you want to know more about my PhD work, it's here in this QR code. There you find my thesis. So yeah, thank you very much for listening.
So the very interesting. We have plenty of time for questions. Have any questions? The micros up. Again, just in I'll start with
thank you very much for the talk. I will shout because it's
fine.
You didn't like everything. I want to ask silly questions about observations.
Okay.
Imagine that you have all of your models predicting them the lines and the abundances, and you then produce synthetic observations of your system in different lines.
Yeah.
Do you have the observational data right now, for example, data of various lines in this kind of systems?
Also, can you repeat the question?
Yeah, and then I'm not connected to the Zoom anymore, I'm afraid.
I think the mic is.
Ah, the mic. Okay, perfect. Yeah. Okay, I see.
Your screen on the camera.
Yeah, I see. Yeah. So the question was about the observations mainly. So, do we have enough data basically to compare lines and other types of observations of our HGB outflows if we would also be able to model this all? We have quite a lot of observations using ALMA, for example, and also not only from CO, but from many different molecules. It's basically, I think, spatial observations, so not only lines, but I'm sure there will be some post-process to really get the lines. The observational side is not really my thing. But yeah, that's a little bit the thing. We have a lot of data from ALMA, from different large programs, and we see all these structures, and also many of my collaborators are working on all these observations. But we really want to go from both sides, from the modeling side and from the observational side, to really come together to be able to predict from both sides what's really going on. For example, yeah, in this Heraclea system, it's a very complex system. We've tried to disentangle it a little bit, but yeah, we're not there yet because we lack some modeling. But we have a lot of observations, yes.
What is the ratio in the envelope between the speed of the wind and the sound speed? So the typical, do we have an idea of this?
I should have an idea about this. I think maybe Lionel, can you?
No, it's subsonic because
it's very subsonic.
yeah, well, you need those pulsations so that you form dust, and then condition pressure accelerates the gas. But initially, no, it's not supersonic because otherwise you just escape from the stuff.
Yeah. So maybe to repeat for the people online, there was a question about the sound speeds in the HGB outflows compared to the expansion velocity. And yeah, we're in a subsonic regime. So we really need these pulsations and the dust to be able to launch the wind.
Yeah, but eventually it becomes supersonic. Yeah, well, it's really, it is supersonic.
Another one?
Yes. Yeah, sure. And do we expect also this environment eventually to be magnetized?
Yeah, so the whole magnetic thing, there is probably some magnetic fields going on, and also people have been thinking about maybe the structures come from magnetic interaction, but I think some research has been done about this, and that the magnetic fields are not strong enough to really make these structures. But the magnetic fields can maybe have an influence. It's a field we're not touching yet, but maybe in the future we can also incorporate magnetic fields.
I've got a question.
Yes.
So this structure is in the continuum, right?
Yeah.
Do we have any idea how? So Silke Maes about the speeds. But do we have any idea about how the speed of the dust streaming through the gas?
As far as I know, it's pretty much coupled. So the speed of the dust is about this expansion velocity.
Close to,
yeah,
because it is streaming at high velocity. This is linearly unstable. It's an instability quite close to the streaming instability, and you might be able to form structure without considering a binary component. But you need very high streaming velocity. So if it's locally high speed.
Yeah, the velocities or the expansion velocities that we know, it's about 10 kilometers per second. So I don't think that's so high yet, because I know like winds at massive stars are about 1,000 kilometers per second. Right. But people have tried different kinds of mechanisms basically to explain the structures, also just in single stars. Yeah. With spin, I think also, and it wasn't able to really make this.
Yeah. It's something interesting to think about, because this is a new instability. It's called the acoustic resonant drag instability. It requires supersonic streaming with dust through gas. Yeah. So that might not be relevant here. But if it is, even locally, it can lead to growth in structure.
It can definitely be also incorporated in all of these structures. Yeah, it's a really degenerate problem. Yeah.
Yeah. Concerning your point, the density is very low. I mean, in the
that's a good thing. You don't actually need. So it's a very low density. You need very little dust. It's not like the streaming state where you need dust to gas at 1 or something. It can work at 10 to minus 3 or something like that.
I think Silke's answer is correct, which is that it's very well coupled.
Yeah. Yeah, because the dust really drags along the gas to make this macroscopic outflow.
You don't have streaming at high velocity.
Yeah.
Yeah, you showed at some point some simulations with where a companion was accreting a sort of a accretion disk around it.
Yes.
Do you think you can capture the chemistry happening there with the tools you showed towards the end?
Not yet. So I'll repeat shortly the question. So the question was about these accretion disks we see around the companion, if we're able to capture the chemistry within these disks. Yeah, the thing is that this is probably really a regime we haven't covered with our 1D chemical models yet. And that's a bit with the issue with Maes or with machine learning in general. You need to have initial data to train upon, and you can only make a surrogate model in this case from things you already have data from. And I don't think we have already 1D models or some kind of chemistry models for this kind of regime. But it's something to hopefully do in the future, of course. But it would be very interesting.
Looks like he has another question.
When you are doing the chemistry, is the number of the number of atoms conserved?
Yes. Yeah.
So, like the number of, if you have a given number of nitrogen atoms,
yeah.
You have the same.
Yes. So in the classical chemistry, the number of atoms and the number of molecules, it's all conserved within the closed ODE system.
Okay.
Yeah.
So you are able to do that and train the coefficients?
Yeah. Yes.
Okay.
Yeah.
Okay.
So indirectly also in Maes, this is not explicitly in there because it's all training and machine learning, but we start from something that really conserves all the number of atoms and everything. So it should be also incorporated in Maes.
Very good one, because
very related to Guillaume's question. I was curious about the details of the loss function. If you're using like a physics-informed approach, we could tie into what you were saying.
We basically just use an mean squared error loss in this case. So the physical approach within this whole system is actually what we do in the latent space. So this is the most physics that comes into it. But apart from that, we're just using an MSE loss, and we try different things to include some of the conservation kind of things, and we also thought about implementing something that really preserves this element conservation, but then we would make the codes more slowly. And so for now we just use an MSE loss, and it worked quite